Ladies and gentlemen, we're going to be talking about the idea of concentration and rate today. And as you remember, concentration is going to be typically measured in molarity. We put it in brackets. And rate we typically measure in molarity per unit time. Could be molarity per second, molarity per minute, molarity per hour, and so on per unit time. And so we talk about rate with how fast reactants can disappear and typically how fast products can appear. That's what we talk about when we talk about rate. And we remember that typically as concentration increases, the rate of a reaction increases. It's one of those four things that can affect the rate of a reaction. Concentration is one of them. So we have a net ionic equation here. We have the ammonium ion. It does look a little fuzzy. It's just my copy here. Reacting with the nitrite ion to form nitrogen gas as a product as well as water as a product. And so this is what we're going to be looking at for our first equation here. And we have some data down here at the bottom on a data table, and I'm going to kind of just highlight what's going on. We're going to be looking at these data tables a lot. So we have one thing is we have 8 experiments that were done, and what's happened is in each of these experiments they have varied the concentration of the ammonium ion, and it is measured in molarity. They've also varied the concentration of the nitrite ion, measured in molarity as well, and they have some initial rates that were observed. Something to keep in mind here, and it's really important for AP, is what's the unit. And the unit in this case is molarity per second. Do not always assume that your unit is molarity per second. As I said above, it could sometimes be molarity per minute or molarity per hour or whatever. So really keep in mind and keep a close eye out on what your units are here. Okay, so I want to highlight a couple things that are going on here. And so first off, I'm going to pick experiment number 1 and experiment number 2. Now the reason I pick these is because I can see right here that the concentration of the nitrite ion is staying constant. They're not varying it. So all they're testing is the difference in concentration of the ammonium ion and what it does to rate. And as you can see right here where I made check marks, we doubled the concentration of the ammonium ion going from experiment 1 to experiment 2. Let's go over here and see what happens to the rate. Okay, so it looks like the rate, which was at 5.4 times 10 to the negative 7th molarity per second, doubled as well, from 5.4 to 10.8 times 10 to the negative 7th. And I know this isn't the correct way to write scientific notation, but it makes life easier for us when we're just quickly comparing these things. So essentially, what are we taking away from this? We're taking away from this that when you double the concentration of ammonium, you can double the rate. Same thing would happen if we tripled it. Triple concentration, triple rate. Okay, we'll stop right there for that one. Now, we're going to go down here and we're going to look at experiment number 6 and experiment number 8 now. Reason I chose those is right here. Now the ammonium concentration is being held constant. And look what's happening here in experiment number 6. The concentration of nitrite is 0.0404, and then it goes up to 0.0808. And let's check out what happens to the rate. So all we're doing now in this experiment is looking at how the concentration of the nitrite affects rate. Rate here is 21.6 times 10 to the negative 7th. It doubles to 43.3 times 10 to the negative 2nd molarity per second. So essentially what it's just told us is both of these reactants affect how fast this chemical reaction is going to go. And so you do not need to copy all this table down. There's going to be some more provided for us. So let's get more into what we're really after. It's such an important concept in AP chemistry. So the next thing we're going to do is we're going to talk about rate laws. And rate laws are an important idea in AP chemistry. So we're going to have this hypothetical equation here, A plus B yields C plus D. And it's a 1-to-1 ratio. That does come into effect later if there's more, but let's just talk about rate laws first. Now, a rate law is well, it takes the form of this. We say that rate is equal to K multiplied by the concentration of one of the reactants. We'll raise it to a power called M, multiplied by the concentration of another reactant raised to the power of N. Okay. Now, in rate laws, and this is the form of a rate law, for this reaction, in rate laws, we only include reactants that affect rate, or how fast a chemical reaction goes. So if a reactant does not affect the rate of a chemical reaction when you vary it, we don't include it in the rate law. Okay? Some more things about rate laws. This idea of K is called the rate law constant. Rate law constant. And something that's super important about K, I'll make a little star here. That's a horrible little star, but that's all right. The magnitude of K changes with temperature. Okay, and we'll keep that in mind. Really, really important. And also really important is those little these guys right here, this M and this N. Now, sometimes students mistakenly think those are going to be the coefficients from the balanced equation, and they are not the coefficients. We call M and N, and it could be any variable, really, it doesn't matter, but we just choose M and N for this case. M and N, these are called reaction orders. Reaction orders. And reaction orders are usually whole numbers. And sometimes they're 0 or 1 or 2 or something like that. Okay? Now, reaction orders have to be found experimentally. Oops, spelling experimental. Found experimentally. We have to actually do a we have to actually do an experiment to determine them. We can't just look at the balanced equation and go, okay, I know what the reaction order is. Okay? Now, what I'm going to do is I'm going to just show you an example of the same exact reaction. Let's say experimentally, and I'm going to show you how to do this here in a little while. Let's say you have a reaction, this is the same reaction, and we found that this was the rate law for this reaction. We found this, and I'm going to show you how to do this later. What would this all mean, and what does it mean? Okay, well, here's what it means. First off, it means that the reaction order for reactant A is 1. We say it's a first order reaction. Okay, the reason why it's 1 is, well, there is no exponent written there, and so it's assumed to be 1. If it's in the rate law, it has a reaction order of 1. For reaction order B, as you can see there, there's a 2 up there, an exponent of 2. And so we would say that this has a reaction order of 2. Now, we're also sometimes asked for what is the overall order of a reaction, and that would just be adding them together. 1 plus 2 equals 3. So we would say overall this is a third order reaction. And you might be thinking to yourself, well, what does that mean, Mr. Camp? I'm not sure what a third order or first order reaction even means. Well, here's what it means. Here's the meaning of orders. If you have a first order reaction, what that means is let's say you double your concentration. You double your concentration. You go from 1 molar to 2 molar. Well, what does that do to the rate? That's going to double a rate. If you triple the concentration, you triple the rate. Quadruple the concentration, quadruple a rate. See how that works on a first order reaction? Of course you do. Now, let's talk about what happens if you have a second order reaction. If you have a second order reaction, and let's say you double your concentration. And the way you would show the doubling of concentration is you would raise it to a power of 2, exponent of 2. And what that would mean, you would be quadrupling. Oops. You'd be quadrupling the rate because it's raised to the power of 2. Hopefully that makes sense. Now, occasionally we're going to come across a zero order reaction. Now, a zero order reaction means we can change the concentration and it has no effect on the rate of the reaction, one way or another. And so if this is the case, we do not write in the rate law. We can just leave it on out. Okay? So, I know this is a lot of new stuff that we've never experienced in chemistry before, and that's okay. We'll do a lot of practice on it, and we're going to start off with the practice right now. Is we're going to use some initial some experimentation to find to do some of this stuff. So here's a classic question, and we'll see lots of these in AP Chemistry, on how to use initial rates to find rate laws in a reaction and what this all means. Okay, so let's kind of walk this through here. I will tell you we're going to do this the long way first, so you know how to do it the long way, and then we'll talk about shortcuts later on. So first off, we have a chemical reaction which has two reactants. We have A plus B yield C. Okay, so we have a combination reaction going on here. We ran 3 experiments on them. Experiment 1, 2, and 3. 1, 2, and 3. We have the concentration of A in molarity, which is 0.1, 0.1, and 0.2 respectively, and then the concentration of B given there. And then we have some initial rates, again noticing that our unit is molarity per second. And we're being asked, write the rate law for this reaction. So that's what we're going to do, is we're going to go through and find out essentially, I can go ahead and write a sketch of the rate law. But this isn't the finalized rate law. Really, when we say we write the rate law, we want to determine what order each one of these are. How do they affect the rate when they get varied? And some of you might be thinking, I can already figure it out. We're going to do it the long way just in case they throw some curve balls at us on the AP test. So here's kind of a long way to do it. We'll do that first. So we're going to first find the order for B, for reactant B. Now, what I'm going to do is I'm going to compare a couple different experiments. Now, if I look up here at B, well, first I'm going to look at A. And if I look at A, I can see that in experiment 2 and experiment 1 and 2, they held A constant. So that's good for me. I can use that information, and I'm going to relate experiment 1 and 2 for B, because I'm really after B. I'm after that exponent on B. Okay, so what I'm going to do is I'm going to take experiment number 2 over experiment number 1. And I'm going to write out a sketch of what the whole rate law would look like. Remember, the rate law is going to take this form right here, rate equals K, and all this good stuff. So what I'm going to do is for experiment number 2, I'm going to go ahead and actually write the rate. So for experiment number 2, the rate is 4.0 times 10 to the negative 5th. And I got that right here. Okay, I'm going to divide that by experiment number 1, 4.0 times 10 to the negative 5th. And I'm going to set that equal to, it's going to be equal to K for experiment 2 over K for experiment 1. I'm going to go ahead and make this really long like this. Okay. Then I'm going to plug in the value for, let's see, we need A first. So A is going to be 0.1 divided by 0.1. And I'm going to multiply that by 0.2 divided by 0.2. And I'm trying, again, ultimately, ladies and gentlemen, I'm trying to find my exponent n right here. Okay, now I've set this up this really long way. I'm going to cancel some things out. Let's go ahead and cancel out 1 and 1. We know they're going to cancel because they're the same. You cannot cancel them if they are not the same values. I'm going to cancel out K and K. I'm going to come back to that guy later. So essentially now I just have a couple pieces of information which are helpful to me. First off, I'm going to divide these two, the two rates, and if you can see they're the same number, we'll divide both of them and we get the answer of 1. Fair enough. Now, next thing I'm going to do is I'm going to divide these two. And I divide both of those, and the answer is 1 raised to the n power. So, what I have to do now is I've got to solve this equation for n, right? So what number raised to what power equals 1? And hopefully from your math class you remember that any number raised to the n power, or any number raised to the 0 power equals 1. So essentially this becomes 1 raised to the power of 0 equals 1, because any number raised to the power of 0 is 1. And you try it on your calculator if you don't believe me. So what we're saying is, we're saying that n is equal to 0. Well, what does that mean? That means for B is a 0 order reaction. We do not even include it in the rate law. Okay? So we're not done quite yet, but we're getting closer. And what I'm going to do is I'm going to go up here, I'm going to recopy my data table just real quickly because I need that down below. It's getting off the screen a little bit. Okay, I'm back with the data table recalculated. Now remember, rate equals K A. Oops, messed up there for a second. Hold on, sorry about that. Let's put B in there. So we're still trying to figure out. We've already figured out what's going on with B. Now let's figure out what's going on with A. So what I'm going to do is I'm going to go and I'm going to choose a couple experiments where B is held constant. B is held constant here. B is held constant there. So I'm going to use experiment 3 and experiment 1. I'm going to put experiment 3 on top, and I'm going to divide it by experiment 1. Why do I do that? Well, I do it for a couple of reasons. One, the concentration of experiment 3, the concentration is greater than the concentration of experiment 1. That's one reason. And the other reason is the rate of experiment 3 is greater than the rate of experiment 1. So I want to have a whole number, hopefully a whole number ratio come out. So again, I'm going to plug in I'm going to use my rate law to plug values in. So for experiment 1, the rate is for experiment 3, sorry, it said experiment 1, but for experiment 3, 16 times 10 to the negative 5th is the rate over 4 times 10 to the negative 5th. It's going to be equal to K for experiment 3 over K for experiment 1 multiplied by A, which is going to be 0.2 raised to the m power over 0.1 raised to the m power. And I'm just for the fun of it, I'm going to throw in B, even though it doesn't matter. It's going to be 0.1 over 0.1, and we know right off there they're going to cancel, and then K's are going to cancel as well. So let's go ahead and solve this problem. Now, 16 times 10 to the negative 5th over 4 is going to give me 4. Okay, I'm going to divide 0.2 right here by 0.1, and I get 2 raised to the m power. So as you guys can probably see, what number, or 2 raised to what number is going to give us 4, so m is equal to 2. Okay, so now I figured out my exponent, so I can rewrite my rate law now. Rate is equal to K multiplied A, second order, and that is my rate law. Remember, B did not affect the rate. It was a 0 order, so we left it out. So what does this mean? It means that anytime we double the concentration of A, our reactant, we're going to quadruple our rate. Okay? Now, the last thing they're going to ask us to do in this problem is we want to calculate the value of K with correct units. I'm going to put my data table back down in here real quickly because I need that. So to calculate K, here's what we do, and it's really easy to do. First off, let's write our rate law. Well, we have our rate law written right here. We don't need to rewrite it. We're going to use this value. We're just going to pick an experiment. We're going to pick any experiment. I always pick experiment number 1 because it's number 1, and there's no reason why I do it, but I just do it. I pick experiment 1. Now what I'm going to do is I'm going to plug values in. So in my rate law, I have rate given. Okay, so in experiment 1, I'm going to plug in rate. So I have 4.0 times 10 to the -5th molarity per second is equal to, okay? It's equal to K, which is what we are trying to find, multiplied by A, because see, A is right there, and here in experiment number 1, it's 0.1. So I'm going to plug in 0.1, and I'm going to raise it to the power. I have to make sure I raise it to the power because it's a second order reaction. We're going to raise it to the power of 2. So what I'm going to do then is I'm going to raise this to the power of 2. Okay. Now, one last thing that I need to make sure that I do, I'm going to include the unit here. And the unit was 0.1 molar. Okay, that's super important. Okay, now we have our setup. Let's just solve it for K. So K is going to be equal to 4.0 times 10 to the -5th molarity per second divided by 0.1 molar squared. Okay, so what I do now is I'm just going to solve this. I need to square 0.1 to make sure I solve it. Okay, so what we're going to do again is we do have to square that value on the bottom. So we're going to square that value on the bottom. So what I get on as my denominator is I'm going to get 0.01 molarity squared, and then we're going to do 4.0 times 10 to the -5th, which is our rate, molarity per second. Okay, so there's our setup. Now, when I go ahead and divide this out, I get an answer equal to 0.004. Now, the important thing here, or we can put this in scientific notation and say 4.0 times 10 to the -3rd. Either way is okay. Now, here's the important designation. We got to make sure we get our units correct here. So let's go and analyze these units here. So check this out. So first off, our seconds here is a denominator, and it is not going to cancel. So we're going to rewrite it as seconds -1st, just like that. Because it's a denominator, we can write it as -1st. Now, watch what happens with our numerators. We have molarity here, and we have molarity squared at the bottom and a molarity at the top. So what I'm going to do is I'm going to cancel out molarity as the numerator, and I'm going to cancel out one of the molarities as the denominator because we only had one molarity on top. So now we have molarity -1st. So it's going to be seconds -1st, molarity -1st, or molarity -1st, seconds -1st. The reason why it's -1st is because it is a denominator in this fraction. And that ultimately is our answer for our rate law constant. Okay? Hope you have a great day today.